Hello everyone, welcome to the course on Emerging Domain Electronics Engineering. This is lecture 5 and in this lecture we will see the introduction of op-amps. As we have already seen the amplifiers, the BJT as an amplifier, MOSFET as an amplifier and FET as an amplifier. Now in this lecture we will see that how this operational amplifier can be used for the analog circuits. So first of all we start with the definition for op-amps. What are these op-amps? As the name suggests, the operations. What type of operations? We are dealing with the mathematical operations like the adder, subtractor, multipliers. We can perform addition, subtraction. We can perform a logarithmic amplifier also. So first, the introduction for operation amplifier. So operation amplifier is a very high gain differential amplifier having very high input impedance, and the output impedance is very low, of the order of, let's say, less than 100 ohms, and the input impedance is of the order of, let's say, mega ohms. So op-amp is a very wide band DC amplifier with high noise rejection, means this device is having the capability to reject the noise. So we can see the symbol for operation amplifier. The symbol is having two inputs. One is called as the inverting input and the another one is called as a non-inverting. So positive we can treat as a non-inverting input, whereas negative we can treat as inverting inputs. Whereas the circuit, the device is having only one output. So we have utilized here only the three pins. One is corresponding to the inverting, one is corresponding to non-inverting, and the other one is the output. So we have the IC which is in the dual inline packaging. Also this IC is a 741 which is having a 8 pins. So we can see, we are already aware how we can see, how we can give the numbering to a IC. Starting from left, this is pin number 1, pin number 2, 3, 4 and remaining 5, 6, 7, 8 to the right. So let me start with the pin number 2. Pin number 2 and pin number 3, these are the inputs. So pin number 2 is corresponding to the negative terminal of the op-amp. So that's why this input is known as inverting input, whereas pin number 3 is basically the positive pin, so it is known as the non-inverting input of the op-amp. Now the advantage of op-amp is that op-amp operates on a dual power supply. As we can say that this pin number 4 is connected to -V, whereas the pin number 7 is connected to +V. So the advantage of this is that we have a higher voltage swing if we are using the dual power supply. Now pin number 6 is the output, and pin number 1 and pin number 5, that is corresponding to the offset null. Later on we'll see in the operation amplifier that although we have connected the input terminals at ground, the op-amp is giving some output which is called as a offset. So offset is a kind of error. So ideally the error should be 0. The output offset voltage has to be 0, but there is some finite output which is available at pin number 6. So with the help of pin number 5 and pin number 6, we can null the output. Null means 0. And pin number 8 is corresponding to NC, which is not connected. So here we can see in this particular figure that we have the dual inline packaging of IC 741. So in industry we just manufacture this 8-pin IC. Later on we will compare the ideal and the practical op-amps. Next we have the block diagram. So as we can say that we have the output, and since operational amplifier is a multi-stage amplifier, multi-stage means we have several stages between input terminals and the output. So if we can differentiate these stages, so the first stage is called as the input stage, the second stage is called as the intermediate stage, the third stage is called as a level shifter stage, and the fourth stage is called as a output stage. So the inputs are directly applied to the dual input balanced output differential amplifier. We will see what is the differential amplifier circuits this differential amplifier circuit is basically formed with the help of two common emitter configurations. If we are placing two common emitter configurations side by side and we are taking output from both the common emitter configurations, and if there is a relationship, something like difference between these two outputs, so that kind of amplifier is called as differential amplifier. So first stage is the input stage differential amplifier, which is a dual input balance output, whereas the intermediate stage is a dual input unbalanced output. We will see what is the difference between the balanced output and the unbalanced output. If we are taking output from both the common emitter configurations, so that type of configuration is called as balanced output configuration. Whereas if we are taking output from only one transistor, only one common emitter configuration, that type of configuration is a dual input but unbalanced output. After that, level shifting stage. Level shifting stage is a emitter follower, which is also called as common collector. And finally the output stage, which is a complementary symmetric push and pull power amplifier stage. So basically it further improves the gain of the operational amplifier. So this is the basic building block of the operational amplifiers. Next, depending upon the inputs, if we are utilizing only the single input terminals, we can see in both the figures that in this first figure we are only utilizing the positive, which is called as non-inverting input of the operational amplifier. So this is called as single-ended input because we are utilizing the single input pin of the operational amplifier. So as we can see here, that if we are providing some sinusoidal signal at the positive input of the op-amp, the output is also in the same phase. Means we can say that there is 0-degree phase shift between input and output waveforms. Whereas if we can see the second configuration where we are applying input at the negative terminal, so what happened? We are getting an output which is 180 degree out of phase. So both the figures, the input waveform and the output waveform, they are 180 degree phase shifted. So this is called as a inverting configuration. Next, now after this single-ended inputs, we are dealing with the double-ended input, which is called as a differential input also. So as the name suggests, double-ended means if we are utilizing both positive and negative inputs, the voltage we are getting is a VD, which is a differential voltage. So if this type of waveform is applied at the input terminal of the op-amp, but keep this thing in mind that we are utilizing both the input pins. So this configuration is a double-ended. So we can say that since there is no phase change, 0-degree phase change is there. So this is called as a double-ended input or double-ended operation of the op-amp. Next, we'll move towards the equivalent circuit. So equivalent circuit basically in an operational amplifier, as we are already aware that the BJT is a current control device, the MOSFET or the field effect transistors are basically the voltage control device. Likewise, we can say here that the output voltage is depending upon the difference of the input voltages, which is, let's say, V2 minus V1. So operational amplifier is again a voltage control device. It's a voltage control device. So we can say that initially we have this negative input, which is the inverting input, positive we have the non-inverting input, and between this we have denoted as Zin, means Zin is the input impedance of the op-amp. So as per the definition, we have seen that operational amplifier is a very high gain differential amplifier whose input impedance is very high and the output impedance is very low. So later on when we'll be solving these cases, then we will put Z in and Z out as per the definition. So here we can say the output is minus A times of V2 minus V1. So inside we can represent the op-amp as a voltage control device. So this is a generalized circuit, generalized equivalent circuit for the operational amplifier. Next, now how we are going to utilize this equivalent circuit to calculate the gain of the circuits for various type of circuit, like for example we have the inverting configuration, we have the non-inverting configuration, we have the summing amplifier, we have the difference amplifier. So this is the equivalent circuit when we have the practical, means when Zi or Ri is high and R0 or Z0 is low. But what happens when this circuit is an ideal circuit? That means this R input is infinite. Ideally this value is very high, infinite, and this R output is 0. So if we'll put R input is infinite, so clearly we can say that this circuit will be open circuit. And here we can see that this is nothing but short circuit. And the output, this can be represented as AD multiplied by VD. Later on we will see what is AD. AD basically is a differential gain of the op-amp. So the op-amp is a very high gain, means the gain is of the order of 10 to the power 6. So this type of operational amplifier is called as open loop. Open loop means there is no feedback. Feedback is something we are taking output, some part of the output, and we are feeding back at the input side. This is called as a feedback. So if we are not providing any feedback, the configuration is called as open loop configuration. Whereas if we are providing the closed loop configuration, means if we are providing a feedback, we are taking output from the operational amplifier and we are feeding at the negative side or the positive side. So based on this we have the positive feedback and negative feedback. If we are applying at the negative inputs, then that type of feedback is called as negative feedback. The examples are amplifiers. Whereas if we are taking the output and we are feeding back at the positive input of the operational amplifier, this is called as positive feedback. So positive feedback basically increases the gain of op-amp. The gain of the op-amp increases, whereas in the negative feedback we can say the gain reduces. So although we are aware that in an open loop configuration the gain is very high and we are not able to utilize this huge amount of gain. So the solution here is that we are reducing the gain, and to reduce the gain we will be utilizing the negative feedback. So there is one more relationship between gain and stability, gain versus stability. As we can say that a circuit whose gain is very high, the circuit is less stable. So if we are reducing the gain of the operational amplifier by placing a negative feedback, that means we are improving the stability of the circuit. So there is a small trade-off. So we can see here that we have placed a feedback and the feedback is represented by a RF, resistance RF, and we have applied input V input or V1 at the negative terminal of the op-amp. So basically we are dealing with the inverting amplifier configuration, whereas the positive terminal is connected to ground. So only we are utilizing the negative input terminal. So this is known as the single-landed input. So we are going to analyze this circuit with the help of the op-amp equivalent circuit. So first of all, let me replace this op-amp by its equivalent circuit. As we can see, this figure A, we have the equivalent circuit where input and output resistances are placed. But if let's say we assume that the circuit is ideal, let's say if input resistance is very high, then we can replace by its open circuit equivalent, and the output resistance is 0, that means we are replacing by its short circuit equivalent, and we are getting an output here which is minus AV multiplied by VI, where VI is a differential voltage applied at the input terminal of the op amp. So if we further simplify this circuit, if we will stretch this circuit, so we can see that this R1 and RF, they appears to be in the series manner. So this we represent as VI, here we have the V1, and also at the output side we have V0, which is nothing but minus of AV multiplied by VI. So our aim is to find out that what is the ratio V0 by V1. So we'll use the superposition theorem. Why I am using the superposition theorem? Because if a circuit is having multiple sources or more than 2 sources, then we can use the superposition, and the overall response of the circuit can be obtained by applying the individual excitation or individual input. So we can say that first of all, out of these 2 inputs, V1 and minus AV times of VI, let's say first we will select source V1, and we are going to calculate what value of VI. So let's say we'll name this as VI1. So VI1 will be, this will be let's say 0. So VI1 will be RF multiplied by V1 divided by total resistance. Now let's say this is our equation 1, and when V1 is 0 and we are considering only minus AV times of VI, then the result will be minus times of AV multiplied by VI multiplied by R1 divided by R1 plus RF. Let's say this is equation number 2. So we have calculated the response of the circuit due to both the excitations, means V1 and minus AV times of VI. So the overall output can be represented as this particular equation, which is equation number 3. So we are further simplifying this expression by taking VI terms to the left, and we are obtaining a result like this. Now one more small assumption I am using, that since AV is very high, if AV is very high, because we are aware that for an operational amplifier the voltage gain AV, the voltage gain which is corresponding to the open loop configuration, this is very high. So we can discard 1 in comparison with AV. Here we can see AV is very high. So we are getting, let's say, equation number 4. Now we want to calculate what is the gain or what is V0 by V1. So V0, we are already aware that V0 is minus AV times of VI, and with the help of this equation of the output and equation number 4, we just calculated the gain, and the gain of the operational amplifier in the inverting configuration is minus of RF by R1. Since we are already aware that this minus sign shows that there is a phase shift of 180 degree between the input and output voltages, and since this ratio is RF by R1, so we can clearly understood that this value, this gain is not very high. So basically we reduce the gain of this circuit by placing a feedback, and the feedback is basically the negative feedback. So this is the most important result we obtain for a inverting amplifier. The gain is minus RF by R1. Now the virtual ground concept. The virtual ground concept, this concept is it's quite easy, as we are aware that the input impedance of the op amp is very high, means when input impedance of the op amp is very high, or ideally it is infinite, then we can say that no current is entered into the terminals or input terminal of the op amp. So if no current is entered, that means it appears that both the potentials are same. These two potentials are same. So if these two potentials are same, then we can say that again the flow of current will be 0. So these two terminals, the inverting and the non-inverting terminals, they are not actually grounded, but they appears that if they are grounded, because the current is 0. So there is a very important point here, that the input terminal of the op amp are at same potential, which is called as virtual short. Or if the other terminal is connected to grounded, naturally the first terminal is also virtually grounded. So we have the term virtual ground or virtual short. So we are going to utilize this technique, virtual ground concept, to obtain various expressions corresponding to the summing amplifier, difference amplifier, integrator, differentiator, and so on, various type of arithmetic circuits. Now we have some specifications. So these specifications include offset voltages. We are aware that offset is a kind of error. So this error in the voltage due to the various input voltages, or the output offset voltage due to some currents. And after these specifications, we have further two more important factors, which is called as slew rate and CMRR. So we'll be seeing that what is CMRR, common mode rejection ratio. So the first thing, as I was telling you, that the op amp output has to be 0 when the input terminals are connected to ground, but in actual there is some offset, there is some voltage appears at the output terminal of the op amp, that is called as offset. So manufacturer basically it specifies some offset voltage corresponding to the operational amplifier. So the output offset voltage is it can be determined with the help of the given input offset voltage provided by the manufacturer. Also this output offset voltage can also be calculated with the help of input offset current. So in this we will be seeing that what are the factors on which this output offset voltage is depending. So first thing, input offset voltage. So how can we represent this as input offset voltage? We can see, since it is a voltage and input offset, VIO, V corresponding to the voltage, I corresponding to the input, and O corresponding to the output offset. So input offset and voltage, input offset voltage. So we can say here that the output of the amplifier, if we have connected positive terminal, if we have connected input at the positive terminal, the gain is 1 plus RF by R1 multiplied by VIO. This is the gain of the non-inverting amplifier. We have seen the result minus RF by R1, and here the result is 1 plus RF by R1 multiplied by VIO. In the later classes we will be seeing all the arithmetic circuits including the inverting and non-inverting amplifiers. So here the output is 1 plus RF by R1, and we are aware that the output of the operational amplifier is V0 equals to AD multiplied by VD, or we can say A multiplied by VD. Here VD is nothing but the VI, the differential voltage applied at the input terminal of the op amp. Now what is VI? We can say that VI is this voltage, means the potential of the non-inverting terminal minus of the potential of the inverting terminal. So VI equals to VIO minus of, what is the potential at this particular point? the potential will be V0 multiplied by Rf divided by R1 plus Rf as per the voltage divider rule. So we have this equation, let's say equation number 1. Now if you are taking V0 to the left and by making a small approximation that the gain of the operation amplifier, the gain of the operation amplifier A, this is very high, this gain is very high, so we can neglect this one, we can discard this one, and the result here is nearly equals to VIO multiplied by A divided by A R1 whole divided by R1 plus Rf. So this A will be cancelled out here, and we can note down that V output offset is nothing but VIO multiplied by R1 plus Rf divided by R1. So we can see that output offset voltage is depending upon the input offset voltage. So this is the first important point here. Next we will see what is the impact of input offset current. So in this figure we can see that this IIB negative and IIB positive, these are called as bias current. These are called as bias current of the operational amplifier. So this negative basically signifies that if the current is entering in the inverting input, whereas the positive is corresponding to the non-inverting input. So we will see that what is the impact of this input offset current. So as we can see that if we are utilizing the resistance value, so we can say that the voltage is nothing but voltage is V equal to IR. So IIB negative multiplied by R1 and also IIB positive multiplied by RC, where RC is the compensation resistance. It is a compensation resistance. Later on we will be assuming some values for this compensation resistance and we will take care of this. So as we can see that we have again two inputs, one is this one A and one is input, this is B. So how we can analyze the circuit, how can we calculate the output? Again we will utilize the superposition. So what the superposition says, again if we have multiple inputs, two or more than two inputs, the output will be, let's say we are considering A source, so the output is nothing but corresponding to let's say if we are considering A, so the output is minus of Rf by R1 multiplied by V input. We have already obtained this result because this configuration will be inverting configuration. This configuration is inverting. Whereas if we are considering B source by neglecting the A source, so we are getting a result which is corresponding to non-inverting. And the result for the non-inverting amplifier we have already seen, it is 1 plus Rf by R multiplied by V input. So the overall offset being V0 equals to, due to the input bias current positive and due to the input bias current negative. So we are getting this particular equation, let's say this is equation number 1. Now the relationship which is IIO, which is input offset current, is nothing but the difference of the bias current of the operational amplifier. So by using this and a small approximation, the assumption that the compensation resistance is nothing but is equal to R1. So the offset is this one. Now if we are neglecting the value of R1, since the R1 is small in comparison with the feedback resistance, generally the feedback resistance is high, so the result we are obtaining is IIO multiplied by RF, means the output offset voltage is depending upon the input offset current multiplied by RF. So if we are utilizing both the expressions, means this expression and the previous expression, so the overall result we can write down is the addition of input offset voltage due to input offset current, and it is due to the input offset voltage. So we can calculate the overall output offset voltage due to both. Now we will see what is slew rate. So again, the slew rate is a very important parameter. A slew rate is a parameter basically specifying the maximum rate of change of output voltage when driven by a large step input signal, something like this, large step input signal. So again, the important point here is that if someone tries to drive the op-amp beyond this particular rate, the output will not be able to change fast. There will be some clipping or distortion in the waveform, means there will be clipping, the waveform will be removed off, some part of the waveform is removed. So mathematically we can say that slew rate is dV naught by dt. If we can see, the unit of slew rate is volt per microsecond. So microsecond means the time is very small, del V naught by del t, the time is delta t, that change is very small. So we will see that for an ideal op-amp, what is the value? We can clearly understood that for an ideal circuit the delta t has to be very small. So if this is very small, delta t is nearly approaching 0, the slew rate will be approaching towards infinity. So for this ideal op-amp, the slew rate is infinite. Now we will see that what is the maximum rate the op-amp can have so that there is no clipping or distortion in the output. So for this particular case, we are basically calculating the frequency, that what is the maximum frequency which can be applied to the op-amp. So if we are considering a case V naught equals to A sine 2 pi ft, where A is the maximum amplitude of the output voltage and F is the frequency. So if we are calculating dV naught by dt, so we are getting 2 pi f A, the maximum value will be 2 pi f A, and the unit is volt per second. And to prevent the distortion at the output, what is the condition? This rate has to be less than, or the marginal condition is it may be equal to slew rate, but it cannot exceed the slew rate, because if it exceeds slew rate, definitely there is some clipping in the output waveform. So with the help of this relationship, we can calculate that what is the frequency. F must be less than or equal to slew rate divided by 2 pi A. The unit is hertz, whereas if we are obtaining in terms of omega, then we are getting slew rate divided by A. So the maximum, what is the maximum frequency we are getting? F max I can write here is F max equals to slew rate divided by 2 pi A, like this. So this is a very important parameter, slew rate. Now we have the differential amplifier. So as in the introductory slides, we have seen that the differential amplifier is nothing but the two common emitter configurations. They are placed side by side. So we have seen what is a single landed input. If we are utilizing only the one input terminal of the op-amp by placing other input to a ground, so that type of operation is called as single landed. If we are utilizing both input pins of the op-amp, it is called as double ended. If the same input is applied then the operation is called as common mode operation. And if opposite polarity signals are applied, it is called as differential mode of operation. So we are going to utilize the differential amplifier for the operation for op-amp. Here we can say Vi1 and Vi2, these are the two inputs. V01 and V02, these are the individual outputs of the op-amp. And if I am assuming that both the transistors are identical, Q1 and Q2, then what happen? If same inputs are applied, if Vi1 and Vi2 both are same, then what happen? The output V01 and V02 has to be same. And if we are getting a result which is something V0 equals to V01 difference of V02, then the output is ideally 0. But during the manufacturing, we cannot manufacture both the transistors identical. There may be some variation due to the temperature and various several effects. So the advantage of differential configuration is that if noise which is common to both, noise can enter at the input terminal from the negative terminal as well as from the positive terminal. So the differential amplifier configuration is very important. That's why it is available at the input side in the first stage. So the noise basically it gets eliminated because noise is common to both input. So we'll be studying what is the common mode rejection ratio. We will see the common mode rejection ratio. It is the ability of the op-amp to reject same polarity signals or to reject the common mode signals and to amplify the opposite polarity signals. Means whatever signals which are opposite in nature, they get highly amplified, whereas the signals which are same at the input terminal of the op-amp, they get highly attenuated. So first of all, we have the differential inputs. Means if we have Vi1 and Vi2 available at positive and negative input of the op-amp, so Vd is called as a differential input. So Vd is nothing but the difference of Vi1 and Vi2, like this. And the common mode inputs means when we are taking the average. So average means Vc equal to 1 by 2 Vi1 plus Vi2. This is called as the common mode input voltage. So the output of the op-amp when both type of inputs are applied can be given as V0 equals to AdVd plus AcVc. So this output is when it is due to the differential mode, this is due to the common mode voltage. So now we are into the common mode rejection ratio. So as I was telling you that it is ability of the op-amp to reject the common mode signals and to amplify the opposite polarity signals. So mathematically it is a ratio, common mode rejection ratio. It is a ratio of AD by AC, means it is a ratio of differential mode gain to the common mode gain. And the value of the CMRR can also be expressed logarithmically by placing 20 log of AD by AC. So you are getting a result here in decibels, dB. So we will see later on in the numerical that the larger the value of CMRR, the better is the circuit operation. So ideally the CMRR is infinite because the common mode gain AC has to be very small, or ideally AC is equal to 0. So something by 0 we are getting a result which is infinite. So we will use this CMRR equals to infinite when we will be seeing the difference between the ideal and the practical op-amp. So by utilizing this equation and the equation V naught equals to AD VD plus AC VC. By utilizing both these equations, first and second, we are getting a result corresponding to the output in terms of common mode rejection ratio. So we will see how we can utilize this result. So determine the output voltage of the operational amplifier for input voltages of V1 equals to VI1 equals to 150 microvolt and VI2 equals to 140 microvolt. The amplifier has a differential gain of 4000 and the value of CMRR is 100 and 10 to the power 5. Means we have two cases. First case is when the common mode rejection ratio is small 100, and the second case when the output is 10 to the power 5. So how can we calculate the output? So first of all, we will be calculating what is the differential voltage VD. So VD is nothing but 150 minus of 140, which is around 10 microvolt, whereas VC equals to half of VI1 plus VI2, which is nothing but 145, and by utilizing the previous equation we obtain the output which is 45.8 millivolt when the CMRR is small. But when the CMRR is high, which is 10 to the power 5, so we are getting a result which is around 40.006. Means the output is nothing but ADVD. V naught equals to nothing but AD multiplied by VD, or we can put nearly equals to AD multiplied by VD, because the output contribution due to the common mode voltage is very small. So next we will see what is the differences between the ideal and the practical op-amp. So as we can see that as per the definition of the op-amp, that op-amp is a very high gain differential amplifier whose input impedance is very high. So input impedance very high means the input impedance is infinite, the value is infinite, and the output impedance is very small. So very small means as low as possible, 0. It is having a very high gain, that means the gain is also infinite. Now we will talk about the slew rate and CMRR. As we have seen that the slew rate of the ideal op-amp is nothing but del V naught by del T, and this is nothing but equals to infinite, whereas the CMRR is also AD by AC. AC is very small, so the ideal value of the CMRR is also infinite. So after this CMRR we have the offsets. So for the ideal operational amplifier, the output offset voltage is also 0. It is also very small. So very small here is nothing but 0. And also the gain of the ideal op-amp is infinite, means it will allow all signals to pass. But practically these are not possible. These specifications are not possible due to the imperfections in the manufacturing of the op-amp. So what happened? The gain what we have seen is infinite. Here it is nothing but, let's say we can say it is of the order of 10 to the power 6 or around, let's say 7000 to 10,000. Practical op-amps means if we are talking about the IC741, what happened? The offset are also non-zeros. Means we are talking about the offset voltages V0 due to the input offset voltage and due to the input offset current. The bandwidth of the operation amplifier is very small, and the output impedance is of the order of 100 ohms only. Ideally we have seen that the output impedance is very low, it is 0, but here we can mark this value as less than 100. Also the output impedance, the input impedance is of the order of mega ohms, means 10 raised to power 6. So this is a brief comparison. And what about CMRR and slew rate? So the slew rate is 0.4 volt per microsecond. For the practical op-amp IC741, the value is around 0.4 volt per microsecond, and also the CMRR is around 60 to 80 dB, 60 to 80 decibels. So this is the comparison, brief comparison between the ideal and the practical op-amp. Now what are the applications? Since there are several applications which includes the negative feedback and which include the positive feedback. So as we have seen, in the negative we have the amplifiers, and here the positive feedback we have the oscillators. So negative feedback, the amplifiers, we have several type of amplifiers like inverting amplifier, non-inverting, amplifier. Next we have the integrator, we have the differentiator, we have the unity gain amplifier, we have the summing amplifier, difference amplifier. Means all the amplifiers are basically under this particular head, which is under the negative feedback. Whereas the positive feedback, we have the oscillators. So oscillator, these circuits are unstable circuits because these circuits are having the positive feedback. Now if there is a positive feedback, the gain is very high, and if the gain is very high, naturally the stability of the circuit is poor. So amplifiers are supposed to be more stable as compared to the oscillators. So we have some common applications of the op-amp, which includes the voltage follower. Now what is voltage follower? We will see in our later classes that voltage follower is nothing but unity gain amplifier. Means the amplifier whose gain is unity, which can be used in the impedance matching circuits. We can make a circuit which is current to voltage converter. We can make active rectifiers. We have the passive rectifiers, we have the active rectifiers, and the whole varieties of filters we have. Filters, we can make the low pass filter, high pass filter, band pass filter, band reject filters. Means a wide variety of filters which are also the active filters. If we can use the resistor capacitors, so that type of circuit is known as, those circuits are the passive circuits. A voltage comparators, again it is a very important application. Voltage comparators, if you want to check that the input voltage is greater than that the set voltages, then it is this circuit is known as the voltage comparator circuits. Oscillators, I have already told you that we have the positive feedback, and some higher order applications which are the Schmitt trigger and multivibrators. So multivibrators are basically the waveform generators. With the help of these circuit, we can generate the waveforms like triangular waveform, we can generate a square waveform with the help of these multivibrators. So these are the applications of op-amp. In the next lecture we will see some other circuits which includes these negative amplifier cases. So these are the references. Thank you.